No, just checking.
Oh, yeah. It looks like there's a delay here.
There is some lag. There will be 3 to 5 seconds lag.
It's not real time?
Sorry?
It seems not real time, right?
Yeah, it has a 4 to 5 second lag. If you are streaming it,
but why it's red? It should be green, right?
No, it's not dependent. So this is going.
Oh yeah, we have sounds here. That means sounds, right? Everything's good?
Yeah. In this you will get real time.
Oh, I see. So the YouTube one is not.
Yeah. In YouTube I set some latency because if you are streaming at live speed it goes only 720p, but if you are having some delay then it goes up to 1080p.
It's not because they are doing some security check background, no?
No. Like you have settings here, so it is not ultra low latency. So I set low latency, which means it has a 5 second lag.
Increase the quality of the streaming.
Yeah, it will be slightly better.
Cool. Do you have any pens? Pen.
Pen.
Yeah, or pencil. Yeah. Oh, thank you. I'll give it like after.
He does more than Stanford, right? Yeah. Yeah, but like, this guy really won. Yeah, won. And I asked him, yeah, I feel like, yeah. I'm just so stoked up. Like, alright, go ahead. But no, I mean, gonna put all our other assumptions that we're building to a human being first. It was kind of hard because like we were like losing days. That was like my sleep. I would recommend that. Yeah. Coast bottle is like the coast bottle is data set that's 106 I haven't heard image processing. There's whole images of this code. Yeah, we found a cool like soccer movie. It's like 500 games. Mainly interface like goals you like automatically. I mean, I'm sure they did. They're like creative with it. Yeah, I know. Like, yeah, man. I'm a soft player. I love soccer here. Like, I'm into it. I don't understand these things. Oh, you know all that. They ever talked about that's my favorite one. That are all together. One might be able to come out and say,
Okay, let's get started. How's everybody doing? Good? Good. How are the project proposals going? 2 thumbs up? 3 thumbs up? 5? 6? Wow. That's a lot of thumbs up. That's good. I had meant to do this earlier. I apologize that it only came today, but I did post a couple of examples, not of the proposal, but of the projects that I thought were good from a couple years ago. And so hopefully you saw the announcement on Canvas. If not, go take a look. I uploaded three project write-ups into just add them to the files on Canvas. So you can take a look at those. They're just meant to be examples. They're not meant to be like do something like this project or not. They're just meant to give you some feel for projects that have been done in the past and ones that did a particularly good job. Just as a reminder, the process is you form a group with 2 or 3 people, no more, no less, and you follow the brief instructions in the assignment about the proposal. Basic information about what you want to do, what data sets exist for doing this, what the metrics will be for determining success, like proposals for the neural network architectures you think you're going to use, and then at least 2 papers that you're going to read in preparation for doing your work, just to give you some background or whatever that it might be, just giving you a bit of a feel for what it's like to do real research in this area. So that's really it. The whole idea here is that you do this pre-thinking, you submit it, your project's not approved until I approve it, and that approval comes in the form of the 1 extra point you can earn in this class. So that's your sign that it's been approved. There's usually a tiny bit of back and forth where I just make some hopefully helpful suggestions so that the project is well scoped and you have a good chance of being very successful on it. So I always enjoy seeing these proposals, and despite the fact there's going to be almost twice as many this year, can't wait. What are weekends for, really? Other than to look at all of your proposals. Anyways, despite the teasing, I'm looking forward to it. Any questions before we get started? Alrighty. Okay, so we kind of start into a new topic. This looks a little bit like what we've been doing. We've been talking about recurrent neural networks, and then we talked about transformers, and this was all mostly in the context of language modeling, and that being kind of the prototypical, or like the standard example of sequential data that you will run into. Though many of you being perhaps scientists of some form or another, you'll see a lot of time series data, and those models are particularly good for time series as well. That since that's sequential data. But we did talk about generative models a bit. Sometimes we call these decoders, and the idea was that there was this way to take these models and take the data and train your model in such a way that you could generate, like for instance, text, right? You could give your model some example text and then have it generate either characters or words, and then the hopefully you trained a good enough model where that generation sort of made sense. Usually it's kind of a fun party trick, but oftentimes even this kind of pre-training, this kind of generative pre-training is good for this kind of learning broad features of the data set so that you can fine-tune your model to do whatever specific task on, say, like a much smaller data set. Anyways, that was all in the context of sequential models. You probably have really missed convolutional networks. I know I have, so we'll come back to these now and talk about generative models or for convolutional networks. So, like, again, coming back to data like images or spatially organized data. We'll talk about. We're basically going to do what we've done in the past, and we're going to see some key modeling ideas here. Things like, today we'll talk about some very basic ones. These will look a lot like character RNNs, where we're going to generate like one pixel at a time. But then we're going to get into things like autoencoders, and then variational autoencoders, and then GANs, generative adversarial networks. You should note that transformers are being used to do a lot of interesting generative models in computer vision, so with images. So again, transformers are very general kinds of networks that tend to have a good inductive bias for learning on all kinds of data sets. But what we'll be doing here is focusing on the kinds of models that have been proposed that use convolutional backbones. So we'll be using all these things will have some kind of network with a bunch of convolutional layers. Oftentimes these are ResNets or things like ResNets. Okay? So, first, just a little reminder of some of the things that we've talked about, but that help us kind of think about generative modeling. So, in machine learning, there's a number of types of machine learning come under these sort of large umbrellas, and one of the big dividers here of different kinds is this notion of supervised and unsupervised learning. Recall that we've also talked about self-supervised learning, right? This was often a phrase we used when we were talking about training, especially the pre-training of transformers in language. Self-supervision is self-supervised tasks are unsupervised tasks, but they're kind of somewhere in between supervised and unsupervised. They have the characteristics of supervised in the way the tasks are. They often are these like classification type tasks, but the data set itself is all that you have. You don't have these additional labels. But anyways, so that's something kind of in between that sort of crept up or kind of came about, in the last 5 years or something like that. That's become a phrase, but nevertheless, there's this big division: supervised and unsupervised. So supervised is kind of like the easy one to think about, I guess. It's often this idea of, we have data samples, some kind of observation, images, sentences, whatever, and then there's some kind of label or attribute or property associated with that. And what we're trying to do is we're trying to learn a function basically that takes you from the input, and you think of like the output of this function as being that label or property or whatever. And that's what we're trying to do. That's what we're trying to do. The goal there is to learn the relationship between X and Y. This is where machine learning really shines in terms of its capabilities, is if you have a lot of data showing you these kinds of pairs, showing you the input-output pairs, then you can start with these really massively over-parameterized function approximators, these neural networks, and via via backpropagation using some signal from an appropriate loss function, you're able to find parameters that do a really great job at giving you that relationship between X and Y. So this is what we spent most of the class doing, right? Classification, regression, all the things around, like, discovering things in images, detection, semantics, segmentation, captioning, the caption being the label in this case, and so forth. It's a very common machine learning task, and it often involves cats, and that's cute. The unsupervised learning, like how you formulate this can be as important as just trying to solve an unsupervised problem itself. So what does it mean when we're doing unsupervised learning? Well, probably the best way to think about it, again, unsupervised means we have no additional labels. We just have the data set itself. So we don't have like images and labels for the objects that are like in that image. We just have the images. So what could you learn from that? Typically what unsupervised learning is about learning the kind of the structure of that data set. Oftentimes you think about it as as a probability distribution for that data set. Meaning, like, of all the, if I give you a set of images, one way you could describe it is, of all the possible ways of arranging pixels, which arrangements of pixels are in this data set and which arrangements of pixels are not in this data set. And we'll develop these ideas as we talk through today, but that's kind of the core idea in unsupervised learning, is that I give you a data set. It's a kind of like manifestation of some underlying hidden structure that describes the data. Oftentimes we talk about these as factors that generate the data. This is where generative modeling comes in. And that's our goal. Our goal is to like uncover that structure by just looking at examples of the data itself. So what are examples of this? Things like clustering. So you may have done, if you've taken any kind of other machine learning course, or you're just interested in machine learning, you've almost certainly come up on clustering. This is, the idea is something like our data set is arranged in such a way that there are these sort of groups of things that look like each other. And there are a lot of different kinds of algorithms for doing clustering, and sort of learning that, like, what are the appropriate cluster assignments just given the underlying structure of the data. K-means, we actually talked about K-means at the beginning of this course. If you hopefully haven't forgotten that, it has been a long time, and maybe it wasn't pleasant, and maybe you did try to put it out here. But we did, we did some programming even around k-means. Just this idea that we expect there to be kind of k-clusters. We learn through looking through the data what the centers or like the centroids of those clusters ought to be, and then we use those to give ourselves or to assign any point in the space to one of those clusters. There's lots of other types of machine learning are just more appropriate, like data analysis techniques for unsupervised learning. One you may not have even thought of before as unsupervised learning is this idea of dimensionality reduction. So, oftentimes our data comes to us and it's like, think about images, it's like this really high dimensional data, right? So you have a whole bunch of pixels, each of those pixels can take on a whole bunch of different intensity values, you've got 3 channels, and all of that kind of has some sort of structure, and you look at it and it's like, hey, that's a dog, or that's a cat, or whatever. But oftentimes, there's a lot of superfluous information in there, especially if all you care about is something like what are the actual objects that are in there. And so you can think of like your high dimensional data as being some kind of like, high dimensional projection from some low dimensional representation, right? And there are a number of algorithms you might have already learned to go into your data and try to learn what are these dimensions, like what are the features that I can take from my data that sort of describe this low number of dimensions or factors, and like how can I get at them. So one thing you're almost certainly familiar with is something called principal component analysis. And this doesn't work so well for images because of sort of the way that information is structured in them, but for lots of data sets, you can do this thing called principal component analysis where you're essentially thinking about the data. You're thinking of the data as living in this high dimensional space, and there's all these dimensions along which it varies. And PCA is about figuring out like, okay, well, which dimension of all the linear subspaces in my space, along which one do I see the most variation, right? The most variation is sort of interesting, right? It's sort of like, in many ways, it's sort of in a single dimensional way, it's capturing the most, like, you could think of it as like possibly the best representation of your data because there's the most variation, and therefore like it's allowing for the most difference between data points. But oftentimes that might not be enough, right? So you can now say, okay, well, now that I know that, I can sort of remove that dimension from my space. That removes the dimension of the space by 1. I can ask the same question again. I'm going to find another dimension within that subspace that, again, there's like the highest variance within that subspace. So it's going to be smaller than the first. Anyways, PCA is this process of figuring those out. And oftentimes it gives you really nice ways of, say, like visualizing high dimensional data, right? You can just work out what are these principal components and then plot in 2 dimensions, sometimes 3 dimensions, just those points, the 2 points from the dimensions of highest variation, or the 3 points of highest variation. And oftentimes, it gives you some sort of really interesting representation of the data. There's tons of other other methods that are like this for taking high dimensional data and projecting it down in 2 dimensions that sort of preserve some kind of structure of the data. But this is very common, and what we'll find as we go through these couple of lectures on generative models is that we're oftentimes going to be doing like what we saw in the encoder-decoder transformers, is that we actually have these 2 bits, or these two parts of our network. We have something that encodes an image, so it's doing a dimension reduction. That's the idea of the encoding. It's like a compression of the data. So think of images, and then compressing that down to just a list of vectors that sort of like is describing what's in that image. And then depending on how we train the decoder, the decoder is then oftentimes is projecting us back out into, say, the original space. When we learn about autocoders here next time, we're going to do this unsupervised task of compressing images and then kind of blowing them back up. And the way that we train them is simply to say the reconstruction of from the decoder needs to match the original image. So it's unsupervised in the sense that there still is a loss, that is the difference between the image and the reconstruction of it from this low-dimensional representation, but we didn't require like another label set or something like that to do this task. We just do the task. So, anyways, lots of examples of this. This is a very common thing to see in machine learning in particular. And if you know something about like information theory and some of like the information theoretic ideas in machine learning, it's the idea of learning itself can be formulated as a kind of compression. That like learning is the act of compressing data to an essential representation that carries, just the pertinent information and not anything else. I mean, that's a very inexact way of talking about it, but there's a lot of great ideas and theories there and ways to think about what we're doing in machine learning. Here are those autoencoders that I had mentioned. Again, the idea is there's some encoder that takes us from high dimensions to low dimensions, some decoder that takes us from low dimensions to high dimensions, and the auto being this sort of self, the auto meaning self here, the idea is that we are training this in such a way that we want the difference between our reconstructed image and the original image to be as small as possible. There's lots of ways of thinking about this idea of like dimension reduction. All right, so again, supervised and unsupervised. So supervised, we've got labels we're trying to learn. We're trying to learn a relationship or a function from the data to the label. In unsupervised, no labels, just the data. The goal, the goal in supervised, again, the function from x to y, from the data to the label. The goal in unsupervised, learn the underlying hidden structure of the data. And then these examples. Now, unsupervised learning is harder. It ends up being much harder than supervised learning because what does it possibly mean to learn hidden structure? If it's hidden, we don't know what it is. So how do we evaluate it? This will be one of the really interesting questions that will keep coming up. Excuse me, as we as we go through these lectures on generative modeling and in this unsupervised setting, is that oftentimes there isn't really a great way to evaluate what's going on here, right? Or to evaluate whether or not we've discovered the hidden structure. And in fact, when it comes to images, you'll find that we often, succumb to the eyeball metric because we just, generate images and we're like, that looks like a great image, and then we're done. We think that's worked, but maybe that hasn't worked great, and maybe even though it looks good to us, maybe we haven't learned the right hidden structure for that data set. It's hard to know. So supervised learning, easy, straightforward. That's why most machine learning sort of starts this way. Unsupervised, harder. Like oftentimes could be ill-defined what it is we really are trying to do, or we might think it's well-defined, but then we get into it and then we're like, hey, I don't know what I'm doing. But anyways, the generative part of what we're going to do sort of sidesteps this a little bit because oftentimes we'll be able to appeal to just, being able to reconstruct our images. So there's going to be this sort of interplay, or reconstruct our data. Images being the primary example, but you know, like you could play this game of what's the smallest dimension for my encoding space that I can use to still get very good reconstructions. You know, you can sort of play this game. Anyways, yes. Oh, I forgot to mention this. Why do we even care about unsupervised learning? Why would we even bother in the first place? If like supervised learning is like easy and straightforward, why don't we even bother? Yeah.
Well, so it's easier and more straightforward in I guess finding the outcome of what you want. But with unsupervised learning, I feel like there's an element of like I've got the data and it's basically in the right shape, just put it in. You know?
Yeah.
Like there's a more straightforward element in that regard.
Yeah. Yeah. Good. Good. Thank you. Yeah.
We can help you find the bias in the data.
Okay.
So
Say more about that.
Like with facial recognition, because all the data was like primarily white people, it couldn't recognize other ethnicities. So this could help you find maybe underlying characteristics that it's looking for to classify that you wouldn't think of with the data collection.
Yeah. Maybe it's going to reveal to us something fundamental about the data that, you know, can help us understand in which ways it might be biased compared to, you know, say other data sets. So yeah, good. Yeah.
Usually, like when we do analysis, we only have like some statistics, like mean or average, or well, those are things like yeah. But as we get unsupervised learning, like in theory, we'd have like the distribution of the data. That's
Yeah.
a lot more information than just like moments or
Great.
anything like that.
Yeah. Good. Yeah. That's great. That's really good. Yeah.
Like what if we don't have labeled data, or what if we don't have enough?
Yeah, yeah. Good point too, yeah. So something like that's on here, right? So it's often the case that we just have loads of data. I don't know, like you stand up a popular website and your web server now has like just tons of logs, you know, just you know, they're partially structured, say, but like all of a sudden, you know, you're just generating all this data about your log. Now, what information's in those web logs? You know, like what do they? You know, like is there anything useful there? Like, can you use it to do things that you care about, like detecting that there was some kind of, I don't know, you know, intrusion on in your website, or like in your cluster of servers that you thought was, you know, cordoned off from like the rest of the world. You know, you might start, I don't know, you might create a device, and then this device is just going to start like logging its observations, right? Like, we live in a world with, you know, enough interesting and cool technology that we're generating loads and loads and loads of this data, but oftentimes this data has no like natural label associated with it. It's just data. It's just, you know, it's like some record of a thing that happened or that we observed. And so oftentimes there is no appropriate label. And if we want the labels, what's worse is that we have to go back through all this kind of these piles of data and then like add those labels. And that's an extremely expensive thing to do. You know, doing so has driven the development of deep learning. So like, thank goodness for things like ImageNet, especially the data set ImageNet, that so much time and energy was spent, you know, labeling the millions of images in that set, because that sort of drove the early days of neural networks, especially in computer vision. But you know, when we get to language, far less language data is labeled, but there's tons and tons of digitized, you know, language. Every single, you know, website in all kinds of languages. You know, all of the work to digitize all of the books ever written. You know, the fact that this has already been happening for, you know, like the Library of Congress and things like that. We just have a lot of just language, but without a label. So we have all this data. So it would be great if we knew we had good ways of working with it that didn't just require us to have some kind of label. In fact, in some sense, you know, this is on here written like this Holy Grail, like, it would be fantastic if what you could do is, you know, have a whole bunch of data about the universe that you care about. Perhaps this is just, you know, your device, or like this, you know, system of connected devices or whatever that is for, you know, whatever that's monitoring. would be great if you could just say, well, yeah, I've got these great algorithms. I'm just going to kind of churn through all that, and then I'll come out and tell you everything you ever wanted to know about that system. And in a lot of ways, we think of like the way that humans learn as very often being unsupervised. Although it's probably more like what we call reinforcement learning, where we explore things, and this is something that will be coming up at the very end of the class, but where we explore and we get rewarded for making good, like doing things that are good with respect to some kind of objective in the way that the world is set up, and then we get penalized for doing things that are bad. It just turns out that we seem to be able to do this really quickly and generalize really well, whereas machine learning algorithms and reinforcement learning are really sample inefficient, and you need to see lots and lots of examples before you learn to do that. So if you could in some ways just kind of take in some data and be like, oh yeah, that's how the world was put together, sort of put together like causal relationships in that world, it would be pretty exciting. It would be a great thing to do. And like, certain labs, like for instance, Meta AI, this is kind of what they do. Although they would call it self-supervised now, but it's it's within the unsupervised learning. Like they're very focused on creating algorithms for doing unsupervised learning, kind of with a goal like this in mind. Okay, now to generative modeling. So again, this is going to be within the under the umbrella of unsupervised learning. The idea is, if we're given some training data, we're going to assume that it's very useful to think of that data as having been sampled from a distribution of some kind, some probability distribution. And again, like the best way to think about this is like, just take images of like a fixed size, even small images, 32 by 32 by 3 color channels. And just think about all of the possible ways in which those pixels can be arranged, meaning you just pick different values for the pixels. That either is, or every one of those arrangements of pixels is either going to be an image that, say, you recognize or that has the characteristics of a particular set. Remember way back when we were talking about CFAR 10, CFAR 100, these low resolution images that had single objects like birds and planes and cars and horses and things like that. Is the arrangement is the arrangement of those pixels such that the image looks like it's coming from that data set, or is it not? And the idea of the probability distribution is that you take that arrangement of pixels, you give it to your probability function for that data set, and it will say, it'll give you a 1, say, if it's very likely to have come from that data set, and it'll give you something near a 0 if it's very unlikely. And if it's sort of somewhere in between, you get a value somewhere in between. But that's the idea, that there is some a useful way of describing or thinking about the data sets that you have as being samples from a distribution. And then what we want to do in generative modeling, as kind of a general framework, is that we want to learn that distribution. We want to learn that distribution either explicitly, so that we can give arrangements of pixels and have it tell us if it's in the data set or not, or implicitly, where we can simply sample from the distribution, and it'll give us arrangements of pixels that are from that data set. So that's what, when we talk about generative modeling here, that's what we're going to be doing. We're going to be thinking about, we're going to have a model for a probability distribution, and we want to learn and make it as similar to the data distribution as possible. Okay? And when you see like machine learning problems phrased in this way, you're in an unsupervised learning land. We're talking about talking about learning the distributions of our data sets. Yep, in true me style, here's the thing I just said on the slide. I always say it, and then here it is later. Apologize. I'm not in sync with my slides ever. Explicit actually assigns a probability to, an arrangement of pixels or just some potential data sample. Implicit, you don't know what that distribution is, but you can sample from it. Why generative models? I mean, first of all, they're just fun, especially when it comes to images. Like, it's just really fun. And if you've played with the models that you can think of it as generative, but these have really more of a flavor of like supervised learning, where you're, like the DALL-E 2 models and the variations on this, where you're giving it text and it's producing for you an image. It's fascinating. It's fascinating to think that these very complex distributions can be learned, and that we can learn to kind of, in the case of these more advanced models, translate between them. And just direct generative modeling, yes, it's fun, but there's often very good reasons why we would want to have some estimation of the distribution of our data. For all the fun reasons, for all the reasons that like these can often be ways of being able to like explore your data set in ways that weren't available to you before you had learned such a model. But like in particular, these methods often require us to learn again some kind of low dimensional representation of our data, and that low dimensional representation, or at least the ability to decode from these low dimensional representations, can be very, very useful in a whole lot of general tasks. Like, again, like what we saw with the pre-training, where you had a model that can then be fine-tuned. Oftentimes you end up in a similar situation where you can say that you've learned the appropriate factors of variation for your data set, and now you can work with those representations to do whatever is the downstream task associated with that. This is very much like the company I work for, Recursion, a drug discovery company. This is very much one of the things that we do with machine learning is through techniques like this to learn the important features of the images that we produce in our lab, which are literally images of cells, and to have a low dimensional description of them that allows you to now ask drug discovery questions that you couldn't ask with the images themselves, but you can ask with this low dimensional vector representation. Things like similarity, things like oppositeness, things like subsets or subspaces that are relevant to particular diseases, and so on and so forth. So this can be a very powerful way, again, to learn a rich and low dimensional representation of your high dimensional data. This is a taxonomy of generative models. Remember what I said, that there's kind of two ways to think about generative models. One where you learn explicitly the density, the distribution, where it can assign a probability to your data being in the training or in the data set or not. Implicitly is more just is the other option, where you don't have an explicit representation, but you can sample from it. So you can generate data from the set, but you don't have a way of assigning a probability to it. And generating from the data set means that you're only ever generating high likelihood data sets, or like arrangements of pixels. And there's a whole bunch of different kinds of explicit density models and implicit density models. We're going to, over the next couple of lectures, talk about these three: pixel RNN, CNN. These are very simple models that look a lot like what we were doing with RNNs. I mean, it's called pixel RNN, so I guess it's not surprising, sort of a basic way to get started here, but we'll then move into variational autoencoders, which are very powerful ways of training generative models, explicit densities for these generative models. And then we're also going to look at these GANs, which are different. This is a model for implicit density estimation. So again, you can sample from your data set, new things that would be likely to be in that data set, but not necessarily have a way of assigning a probability to an image. Okay? So that takes us to pixel RNN, pixel CNN. So, questions so far? Yeah.
Could you clarify the difference between explicit and implicit density?
Yeah. So, remember a couple of slides ago we had like P data, and that was the probability distribution for our data set. Okay? Then we had P model, and think of it as like a neural network that can do one of two things. It can either assign a probability, it can assign probabilities to, again, just think of images for a second and to say, to arrangements of pixels, to say, if the probability is high, that arrangement of pixels is likely to have been in our data set. If it's low, it's likely not to have been in our data set. That's explicit density estimation, because you're actually learning the density or the distribution itself. Implicit is the other one, which is instead of a neural network actually like being the probability distribution or density, the neural network's job is actually to simply generate images from the data set. So they're both ways of having estimated that, using P model to estimate P data, but one you can use to assign likelihoods to being in the data set, and the other can only sample or generate for you samples that are likely to have been in the data set. So it's implicit in that case because you don't have an explicit representation of the density, you just have a way of sampling high likelihood samples from it. Did I answer the question? Okay. Other questions? Yeah.
What form, so for explicit density, what form would our representation of the distribution end up taking? Because it's not like I'm writing down.
It's literally a neural network, right?
Okay. Yeah.
And its output, in the simplest version, its output is something between 0 and 1. But a sigmoid maybe, the thing I said never used, at least not as activations, but it's something useful in this output in the sense that it's going to take in images and it's going to output probability. And that literally is going to be a probability to say, are you likely to have been in the data set? Meaning, do you have the characteristics of this data set? Not necessarily that you're like an actual training example within the data set. That's not the task. That's an easy one. That's memorization. This is like, can I learn the characteristics of what it means to be in this enough to assign these probabilities? So it's literally just a neural network.
Yeah. Sorry, quick follow-up.
Yeah.
So just to accuse things a bit.
Yeah.
If you were thinking about what a PDF would look like for a probability
Yeah.
function, the explicit versus implicit, a PDF for explicit would just be the actual PDF, right?
Right.
But for implicit, it would just be a bunch of samples. This space.
Yeah, that's right. That's exactly right. Good. Yes.
I think specifically, isn't it that explicit densities are usually like transformations of random variables? Like in variational encoding, you have like a bunch of normal distributions, then neural network transformation them to be your network or your distribution.
Yeah. This is true also in the GANs as well, which is interesting. So, like an implicit. So, you actually train GANs in very much this way. It's true in variational autoencoders you do, but what's interesting is like, again, if almost always for all these problems you can kind of formulate them as, well, does it have an encoder and a decoder? Well, then it's probably an explicit density. But does it only have a decoder? Then it's probably an implicit density. and when we get to GANs, you'll see, like, it's basically, you're literally learning a transformation from some very nicely behaved distribution like a Gaussian, you know, some higher dimensional Gaussian, not as high dimensional as the image, and then you know, you sample from that, but that sample then gets transformed into a sample from the, you know, like your image distribution, which certainly is not Gaussian. It's going to be have all kinds of crazy, you know, spiky modes and things around, you know, arrangements of pixels that are, you know, very much from the data set, but like very nearby. You know, like the image might get a little bit blurry, and so you don't want that. You want to assign low probability. So it's using the power and the capacity of neural networks to do this kind of like implicit transformation from a very simple distribution to a very complex one. Yeah. Cool. Other questions? All right. So these are simple. They're meant to just kind of get us thinking about the problem and you know, like what's been done and how to evaluate them. And they're literally going to be an RNN that generates pixels and then a CNN that generates pixels. So what would that look like? Well, first things first. So really kind of like before everybody was doing neural networks, there was a lot of machine learning was on things, using things like what we would call probabilistic graphical methods. And what these often were just ways of thinking about how the variables in your data set sort of depended on each other. So you'd have, you know, this probabilistic graphical model is something like, you know, each node in this graph, this is like a mathematical graph, being, you know, one of the like parameters, or one of the values in your data. So again, the way to just continue to think about this is like the pixels within an image, and then how do those pixels depend on all the other pixels? And you want to like somehow try to model all that, and then, you know, use certain, I don't know, use that information about that graph to then put all that information together to compute this explicit likelihood function for your data. So an example, so like one of the probably like easiest to understand here is something that we would call a fully visible belief network. And the idea here is that we can factorize like the values in our in a single data point. So like the pixels in our images. We can factorize this distribution. So the thing that's going to assign likelihood to a full image into something like this, where you know, we pick some arrangement of pixels. Just think about like kind of a raster ordering, where we just, you know, start with like the top row of pixels work from left to right. When we get to the end of the image, we start over and the next row of pixels down, and think of that as like as a total ordering of the images, or of the pixels within the image. And we can say, well, you know, the first pixel will have some sort of prior distribution of like what values it ought to take. But once we've fixed a value for those pixels, then we can start to say, okay, well, the next pixel in the ordering is going to be conditioned in some way on having chosen that, right? So like, I don't know, if this pixel is black, it would be very unlikely for the very next pixel to be white, right? So the probability of that, you know, of the second pixel being white would be very low. That this would assign a low probability given that. But if, you know, if this was black or something close to black, then it would be high. And then once we have two of those values determined, then the third one's going to depend on those two, and so forth. And you can see, and so it's a way of factoring this distribution into sort of like the dependency of the pixels on each other. It doesn't necessarily mean that this is like the right way to model it. It just is a model and that is like internally consistent, meaning like, you know, this can't, like, this does equal this in terms of like the way that we can factor probability, like the conditional total probabilities into conditional probabilities. Like this is just a, I think this is called the chain rule probability. It's probably in my slides. No. Oh yeah, it is my slides, right there. See? At some point they got written down, yeah. But whether or not I remember them, I have no idea. So anyways, this is a way of thinking about this. And this has a kind of generative feel to it, right? This is saying, if it's, you know, if this is a decent model for the explicit density distribution of my data, then, you know, perhaps I now have a way of learning this this conditional dependence. And what do we do? Well, what we do is we parameterize these conditional distributions as neural networks. We basically are going to say, this is a neural network, and we're going to learn to do this very much in the same way that we learned to do this for sequential data. This is now spatial data. This is why this is maybe not a good model, because we're using kind of like an incorrect inductive bias in the way that this is set up and how it's conditioned on other pixels, but it's not inconsistent with like the rules of probability, so we're good. So we're going to use neural networks for that. You know, this does require us to define an ordering. You could do simple raster ordering. There's other more complicated. There actually was a paper called Pixel RNN in 2016, and it literally used an RNN, namely the LSTM that you know about, and it picked an ordering for the conditional for doing this kind of conditional learning by starting in a corner and then kind of working your way out from those to others. So the important part to note here is that this pixel right here depends only on this pixel here. But this pixel here depends on this pixel and this pixel. And of course these two pixels depended on that pixel. And this is kind of how you get this factorization. You just kind of keep moving. And then, you know, you can learn to do this, right? The task here is simply, this is actually a classification task, right? Like pixels, you know, you might think of them as, you know, being like as being continuous, but they're not, right? There's, you know, it depends on like the bit depth of your image, but you know, there might be 256 potential intensity values that your pixel can take on in an 8-bit image, and one, you know, one for each channel. And so you really have a classification task. So you're just saying, like, you know, there's just some way of kind of sampling this first pixel, and then you can learn, given that pixel, what this pixel's value ought to be, and then given these two pixel values, what this pixel value ought to be, and so forth. And you can do it with an LSTM because you have this ordering. It's not like this worked great. It just, in some ways it's like a demonstration of what could be done, translating models that were developed for certain data types to others. But in fact, these methods are really, really bad in terms of like the images that they end up generating. Nevertheless, this can be done. There's many drawbacks besides having generating low quality images. Sequential generation like this is super slow. If you think about it, like there's hundreds of thousands, possibly millions of pixels in large images, and like, you know, this kind of being able to generate that many tokens is very, very slow. Not to mention that like LSTMs can't possibly be conditioned on, you know, hundreds of thousands of previous pixels. You know, if you remember, we talked about them possibly doing well on 20 or 30, and if you added attention, maybe even longer. But you know, in general, like one of the reasons transformers were introduced is because they do a much better job at learning long-range dependencies. So you might think, well, we should have done transformers. In fact, transformers come out in the next year. or something else. But the same group said, okay, well, maybe we can do this exact same thing with instead of the dependencies coming from these sequential definitions, maybe we can use a CNN. So this is done in almost in almost the same way. The difference here is that when we learn these conditional distribution functions of like what should be the pixel value that we choose here, we actually use convolutional filters so that the pixels that we use to generate this are in a spatial region near that pixel. And you can see this kind of picture. This picture is a little bit weird, right? Because like our filter really, we often think of these filters as being centered at this pixel, and then we learn something like weights around it to incorporate or integrate the information around that pixel. But we're trying to do this in a way that's generative, right? The whole reason we even set these things up is that we're trying to learn to generate images. So what this does is this does the very same thing where you pick an ordering and you sort of start like say up here in the top left corner, and then how do I get the pixel value here? Well, I'm going to do some kind of padding around this. I'm going to center that thing, at the pixel I want to generate, and then it's going to incorporate, say, lots of zeros, both for for all the pixel values that are coming afterwards, and in the padding. And I'm going to learn to do this classification problem again of choosing the correct pixel values. But again, the bias here being using convolutional filters rather than some kind of like strange ordering of the pixels like we just saw in the previous image. So that's just a different model. It looks like a convolution. It's just kind of weird because you're going to do this. You're going to do again this kind of very slow generation, and your filter is kind of weird because it's never learning anything down here. This is yet to be determined. So again, to make this generative, or what we often call autoregressive, in the sense that the next thing depends on the previous things. You have to sort of mask this, mask what the filter is taking in. I think there was a question. Yeah, Chris.
You can change what the shape of the filter is going to be based on like how you model the probability distribution of X, right? You just said that the probability distribution over a single pixel is only dependent on its neighbors, like a little square, then the filters would be squares, right?
Yeah, right. I mean, like this very much is going to look like what we did before when we weren't thinking about generation. These could be 3 by 3 or 5 by 5 or 7 by 7 or whatever. In fact, I can't remember exactly, but in this paper, I believe these are quite large, so that there was a lot of like information integrated to pick that to choose that pixel. But the point is that like really this filter is not like the full, I don't know, call it 7 by 7 filter, because these weights never do anything. Like the weights that would typically be here in your full convolutional model, they never do anything because all the pixels out here are masked, so that we only generate given pixels that we've already that have already appeared in our generative process before. It's this idea of conditioning again on some idea of previous pixels, whether that and you basically we're just defining what previous means. So makes sense? Is the questions? Yeah. So there's this factorization here. I have some examples of this, I think, coming, yeah. So what's good about this? This ends up being a bit faster than pixel RNN, because instead of this, like having to do this generation and use all these previous pixels, it's only going to use these kind of spatially localized pixels. And there's some notion of being able to train this much faster because of being able to do some sort of parallelization that takes into account the way that these previous pixels are arranged. Still very, very slow, and I guess you can't see it too well. If you get on Canvas and you look at these, you can go look at these more closely. Just they're low resolution already. But what you have here is a pixel CNN trained on CFAR 10 data, which is already 32 by 32, and then you have over here a pixel CNN that was trained on ImageNet, but the ImageNet images were cropped to 32 by 32, again because the training is so slow and kind of onerous for these models that using large images would just take way too long. So you have small images. And if you just look at these kind of like from where you're at, like on some level they kind of look like the things, if you remember, that we saw in CFAR 10 or in ImageNet, right? Like they kind of look like images of natural scenes, right? And just if you're kind of like glance out of your corner of your eye, like, oh yeah, like that's probably a photograph of something, But if you kind of like me, you're right next to the image. You kind of look at it. Every single one of these things is like complete nonsense, like just complete nonsense. Like there's nothing that makes sense in any of them. To see that you have to literally, you're gonna have to get on canvas. You have to like zoom in. But maybe you already can get a sense of that. Like just pick any one of these. Just like I'll randomly go like this. Okay, this. There's like some green stuff here. Like that looks like the green of grass or trees or something like that. And it's kind of in a background, right? It's like around the edges. And there's kind of a foreground thing here. It's kind of a cherished thing. You can see through it. I don't know, like it's really, really bad. I have no idea what's going on here. Yeah, there are 2 questions. Go ahead.
So for this, it looks like you've learned existing data set. And then for generating it, after you've learned your model and your weights, how do you kind of generate it? Does anything go into it?
Yeah. Okay, good question. So this is exactly like what we did for language. So once you've learned these models, again, you're learning the conditional probabilities of like what should this particular pixel value be, given the fact that we've already determined all these other values for pixels that have gone before, that are previous in some sense. The way that we do the generation is we literally, we randomly sample, say, like the upper left-hand corner. And then we generate the next pixel with that information. Now we have 2 pixels. And then we generate the 3rd pixel with those 2 pixels, and so forth. Right? And each time, remember, we've learned a distribution. So we do exactly like what we've done before. Like that's a distribution over a finite set of possible pixel values. So it's going to assign likelihoods for each pixel value, and then we're going to just sample from it. So we're going to more often pick the pixel values that are assigned high likelihoods, and we're going to not pick the pixel values that are assigned low likelihoods. But every once in a while we might pick one with a low likelihood because we might do enough generation where that just is going to happen. And then that's how you do it. You make one of these like crazy, I have no idea what's going on images. But it has learned something. It has learned something. Like there's some like kind of gross statistical correctness to these images, right? Like there very often there's like a foreground and a background, and the color distinctions. There's like gradients to the colors. There's like textures, like fur textures, and there's like metallic textures and things like that. But like as coherent, like semantically coherent objects, there's just not a single semantically coherent object in there, because these things haven't learned that. They don't really have the capacity to learn that. And that's what as we're going to move on to other methods, they're going to increase the capacity. Also, like they're going to end up being much better models for just like learning these kinds of conditional distributions, and they're going to be trained in other ways, and they're going to get much better at being able to kind of learn to generate these kind of semantically coherent things until we get to, you know, these big GANs that generated that, you know, I don't have a picture right now, but those amazingly high resolution images of faces, right? If you remember that from the beginning of the course, they're, you know, like those were generated portraits. That person doesn't exist, but it looks like exactly like an image, like a high resolution photograph of of someone's face that you would have taken with, you know, a high quality phone or some kind. I think you had a question, and I'll come over here.
Yeah, so I guess I was just going to clarify. So this is unsupervised. You're right that they're saying this is unsupervised. So, for example, CFAR 10, it's not trying to make a plane or anything like that. It's purely this is what pictures look like.
Yeah, exactly. And how does it learn that? It's learned that by learning a dependency of, like, you know, if I have all this arrangement of pixels, then the pixel here is most likely to be, you know, have this value of intensities, right? That's what it's learned. And the thing is that when you learn these things with LSTMs or with these you know, with the CNNs, they're not powerful enough to learn to incorporate like long range pixel dependencies to become coherent, like semantically coherent objects, like a cat and things like that. It's learned to say, like, yeah, I got this arrangement, so I'll put a pixel there that is statistically consistent. But, you know, it's consistent, but you know, it's like if you think of like your ability to learn, like increasing capacity to learn like higher and higher frequency features, but in like this kind of abstract way of thinking about features, it's learned low dimensional. It's learned like low frequency features, like it's learned it's learned background and foreground. It's got very low frequency kind of thing, right? But it hasn't learned to then take these like higher frequency things and turn that into like a cat, you know. It's learned to just give you some cat fur disturbingly here, you know, without the rest of the cat or whatever.
That also reminds me of like a block test kind of thing.
Yeah,
like,
right.
What do you see?
What do you see here?
You
Yeah.
have to
This could be your project if you're a psychology major or something. What do you see in these generated images? And you can manipulate what images get generated for whatever evil purpose you have as a psychologist.
So I'm still kind of trying to wrap my head around like the training of this.
Yeah.
So is the loss, like as you're sliding this convolution along, is the AI trying to predict what the next pixel is going to be?
That's it. That's it. It's exactly the same thing as like if this were a sentence, what should the next word be? And I'm given examples of sentences, or in this case, I'm given examples of images, and the way that like and their particular arrangements of pixels, right? And that's why we can say, you know, here's a model trained to produce things that were in CFAR 10, and here's a model that's trained to produce things that were in ImageNet, because this model was trained on the CFAR 10 data set, so to produce the next pixel depending on previous pixels, but from that data set, and this one from here. So here, what we should see, if this was good enough, is we should see lots of planes and horses and cars and ships and things like that, birds. And here we ought to see, I mean, it's 32 by 32, but here we ought to see like thousands of, you know, the 1,000 different classes that are there. We ought to see like various species of dogs, and we ought to see various species of flowers, and we ought to see, I mean, there's so many different objects there, right? But so that's it. So like, if this was perfect, it would learn to do that. But these models do not have the capacity, like neither in like the size of them nor in the ability to incorporate long range dependencies of like the current pixel on, say, like all the other pixels. Plus, this just kind of inductive bias that's forced on you to generate these images, you know, literally in the RNN case, but like this kind of sort of faking it with the CNN. Like this is just not a good inductive bias for learning those kinds of dependencies. So we need other methods. We're gonna look at other methods. Good questions. Other questions? I think actually we're at near the end. Yeah, this is the end of it. So, are there any pros? Well, there's a couple of. It says good samples. Those are not good samples. They were good samples for 2016. They're really bad samples now. But they are ways of explicitly computing the likelihood function. So if like for some reason you really need to learn that likelihood function, then this is a way of doing it, but it's not going to be a very good estimator because it's going to, again, it's going to say things like this look like, you know, are an image that, and I don't know what kind of weird tire sort of thing that might be. What's that?
Donut.
Yeah, like metal donut thingy. But it is a way of learning an explicit likelihood function. We are going to learn other ways next time, and this is going to be variational autoencoders. The con, actually the samples are bad, and the sequential generation is just super slow. Yeah, so that's it. So next time we will do variational autoencoders, and this requires a bit of math, a little more than we've had to do so far in this class. We're going to have to like push integrals around a whole bunch, and hopefully that won't scare you off. Hopefully you're pumped for that, ready to use a Jensen's inequality here and there, and then we'll get this really cool computable estimator for these complex distributions. So good, we're out 5 minutes early. I'll be sticking around if you have questions, you want to talk about your project or whatever. Otherwise, I'll see you on Thursday.